Recording. So we're going to talk about abstract data types, which is kind of a strange concept. I'll try to give you a sense of it, and then we'll start looking at data structures that kind of live in parallel to some of these abstract data types. So today we're going to talk about one abstract data type called stacks. Pretty simple concept, but it gives us an opportunity to sort of talk about the difference between the code and the kind of interface to the code. And it might just shed a little bit of light on our thinking when we talk about the difference between abstract data types and data structures. It's a little bit murky sometimes. The truth is there are certain things that kind of could be thought of as both. So we'll try to unwind that a little bit for you as we go through this. Quick announcement. So we'll have a stack array class. So we're going to very quickly jump into C++ class development and a little bit of pointers. So I'll start you off with some reminders on how that stuff works. Take it slow. You'll have time to sort of get comfortable with this part of C++ if you haven't used it before. But till we get to our next big homework assignment after homework 2, you won't have to do a lot with this stuff. We have a lab 8, which is implementing a queue with a stack linked list. That's going to be on Thursday. And then we have, of course, our lost amulet and our quiz 2 coming up. Okay, so this is a part of the course where there's going to be a lot of pre-written code, and I'll try to minimize that as much as I can. But our focus, as always, is the ideas behind these, data structures and algorithms, and we don't want you to have to reinvent the wheel. Many of these things have been written 1,000 million times already. So I'll be giving you a lot of sample code, and like today, asking you to fill in some blank space is really just to kind of help you remember the key parts of this. Now, just some reminders. I hope I got these right. I had some wrong. I'm kind of updating them. So Friday's last day to drop. I'm reminding everybody of that in general. Our midterm will be in class on Thursday. I'm pretty sure that's October the 16th. I had that wrong earlier, but it's really basically lecture 16. Which is always even number lectures are always going to be on a Thursday for us. So that's kind of midway through October. And that is an in-class only exam for those of you who haven't had one of these exams with me before. And there's only one try. So every once in a while somebody says, wait, I thought I got 3 tries in the midterm. So it's only a one try thing. So please do clear your calendars and let me know if you think you're going to have any problem with that ahead of time. So appreciate that. In your code, I think everybody's been pretty good, but clear indentation, getting rid of dead code and dead comments is good. Sometimes when I run some sample code, we got to test large samples of n, right? Like, 250,000 values. So if you've got a print statement in your code, I got to go take that out. Otherwise, I can obviously never kind of run that thing. So keep that in mind as you go through those, and write code that you're okay with people seeing. Stuff like that is good. Stuff like that is fine. Even stuff like that is okay. Putting stuff all in one line, just kind of use common sense on that stuff. That's just fine. Even stuff like that is kind of okay, but it starts to be a little hard to read if I got to debug stuff. So keep in mind that you can always just hit the tab key and make things a little bit better for everybody. Okay, so today we're going to talk about stacks, a little bit of C++ code refresher. We're going to get a little bit into dynamic and automatic memory allocation. Now, this is not intended to be an advanced C++ class, but will try to use this language, so you're familiar with it when it comes time to actually, dig in deeper on the C++. The big topic today is abstract data types. So the idea behind abstract data type is it's a general description of a problem and kind of an interface to solving the problem. So it sounds very fluffy and hard to nail down, but I'll try to give you some good examples here to start out. And then we'll look at how object-oriented languages kind of help us design solutions in a abstract data type kind of way. So there is kind of a correlation between the methods and the constructors of classes and this idea of an abstract data type. So let's take the stack of pancakes. We push one on, we push another one on, we push another one on. We don't serve pancakes from the bottom. So the idea of a stack is something we could model in a class in any language, but we haven't really figured out quite how we're going to store each pancake. Like that's not really something we're worried about when we talk about the abstract data type. It's more about the idea of stacking pancakes on top of each other and unstacking them. So we'll look at the correlation between this idea of an ADT, or an abstract data type, and the interface, or the methods in a particular class. So we'll look up, or kind of design a generic interface, and then we'll put some actual implementations on it so you can see what the code looks like. We'll also look at some really nice uses for having stacks. So there are some useful algorithms that are based on the idea of a stack, regardless of how we implement it. So Dijkstra, who was kind of one of the early developers of algorithms, came up with this two-stack algorithm for dealing with equations. So we'll look at that. And then we'll look at some implementations via arrays and the ramifications on performance of using an array as opposed to, let's say, using a linked list, right? If we use a linked list to implement a stack, what's the difference going to be over the long haul than if we use an array? What are the pros and cons there? So we'll just kind of do a light pass over the top of that. And then you'll have a little exercise, really a very small lab, to kind of make sure you're comfortable with how we do this stuff in C++. So not a lot of stuff today. Very quick review. We'll take one more look over our shoulders at the two most efficient sorting algorithms we saw. These are really the only two ones that are n log n, right? Or what we call linear arithmetic, okay? They do the divide and conquer, and they are recursive in nature, but could be done in for loops as well. And remember that the merge sort is from the bottom up. So we go all the way down to the leaves of the tree and then put things together on the unwinding phase of recursion, okay? So 1 and a 1 get merged, then a 2 and a 2, etc., which is different than what we saw with the quicksort, where we partitioned around a midpoint and then we slowly partitioned the left half and the left of that and the left of that. So still divide and conquer, just took a different approach to doing that. And both of these have different performance characteristics. The primary difference is quicksort is unstable, but doesn't require extra memory, and merge sort is stable, but requires twice as much memory to actually accomplish the sort. So there's always a little bit of trade-off that we get. But those are our kind of benchmark sorting algorithms. Anything less than that or worse than that, like a bubble sort or a selection sort, those are quadratic, and we tend to try to move beyond those things pretty quickly. Okay. And then high level, though we won't try to memorize this because it's on the internet. These are kind of just a table of performances. Remember, we're always talking about worst case, best case, average case with respect to something like swaps or time or copies. So it's always important to sort of qualify, when we're thinking about this stuff. Well, what are we measuring, really? Could be time, could be swaps, could be just recursive calls, right? So it really kind of depends. But fundamentally, in the world of sorting, n log n is kind of where we want to be. That's our gold standard in the middle. And so we'll look for things that are kind of better than that if we see them. But generally speaking, we're probably not going to get much better than that unless we do something like a counting sort or a bucket sort, which relies on constraints. And some of you did some really great work around that. But generally speaking, open-ended data sorting is going to be at an n log n kind of situation. So let's kind of move ahead then. So C++ code and just some reminders about language. I tend to color my variables in light blue, and I'll try to color dynamic allocations of memory in orange. This is just something I've been doing for a while. Help me and help you kind of differentiate between what C++ is doing. Because a lot of this stuff is hidden in other languages. It happens kind of behind the scenes. But C++ kind of puts it in our face a little bit. So one of the key things to remember is that whenever we have a pair of curly braces and we create a variable, that variable is what we call automatically allocated. We didn't have to say new or malloc or anything like that. It just kind of happens. But it's going to go away as soon as we get past the bottom of that for loop. So the string response variable is automatically allocated and then automatically destructed. And that's a really nice thing. We would say it kind of goes on a stack, so to speak, not unrelated to the stack we're talking about today. And we can use it, right? And then we don't have to worry about it anymore. Such that if we try to print it out, of course, we're going to get some kind of a bug, right? It's like, hey, I don't know what that is. That is what we mean by automatic. It comes and goes in the boundaries of the scope in which it was created. And that's a nice, pretty clear rule, right? And most programming languages kind of have those kind of scoping rules, okay? So something like this is kind of interesting. So I've just created some, random scope there. It could be a while loop or an if or something. But if I create that array, it comes and goes pretty quickly, right? Kind of enters and then it goes away. And we don't really have access to it after we leave that scope. But if I were to do something really sneaky like this in C++ and say, oh, okay, well, this thing is not pointing to anything, but right inside of there, I'm going to enter some scope. I'm going to steal the pointer from the array, which I can do because primes PTR is really just a pointer to an integer, and primes the array is really technically also pointing to the 0th position of that integer right there. So they really are pretty close cousins. So I can steal that pointer, and then once the scope is gone, I'm now left holding on to a pointer, which is exceedingly dangerous, right? Because the memory is now gone. So most of the crash bugs and the nasty late night bugs we'll be chasing in this class will be because of situations like that, where we maybe accidentally have a holder on piece of data that is going away because it was not meant to stick around very long. It was very transient, okay? So this variable kind of exists outside of that scope. So it's not going away, but the address that it's holding on to is no longer valid. And so if I were to say, hey, try to use that pointer as an array, we could very well get a crash, okay? Now we might not. C++ is like a car with no airbags and no brakes and no bumpers a lot of times. So it might give you the data, specifically number 11, and you might say, oh, my program's just fine. But the more you keep walking along that path and using that primes PTR later on, the more dangerous you get. And in fact, we never really want to actually do something like that in the first place. Right? So what we really ought to do is, basically never kind of steal pointers like that out of the middle of the scope, and will kind of keep us out of trouble. Okay, so that would be pretty unusual thing to do, but every once in a while we do it accidentally. Now, in contrast to automatically allocated arrays, right, we can dynamically create an array on the fly using the new keyword. So again, I put that in orange as a little clue. So we're saying I want an array of 5 integers. Okay, so it's a little bit of a strange way of saying that, but we're getting an array of 5 integers, and indeed, primes PTR is an address of an integer. So new will always give us an address. So whatever we're going to put that in better also have a star in its allocation type, right? Int star, float star, whatever, right? Here we got int, so this must be an int star to hold on to that. So there's our new array. And we haven't initialized it, but we've said it's got 5 spaces. And so now we can do all the good things like initialize those. And notice we're treating this pointer like an array. So what is that square bracket doing for us? It's really just kind of like hopscotch. It's saying, oh, jump 0 to get to that. Oh, jump 1 integer. Oh, jump 2 integers. So the square bracket is really just like a little math for addresses. It says jump that many integers over, and that's a pretty low level access, which is one of the reasons why arrays are so efficient. We're just sort of hopping over integers in memory, literally, transistors in your computer, at a microscopic level, and getting to the location we need to read that value. Okay? So in a very real way, pointers to integers, have the potential of acting like arrays as long as we allocate that memory for them. Okay? And we call them pointers, but of course, there are no pointers, there's just addresses in memory. And then as someone pointed out, I think I had this wrong in some earlier slides, terribly embarrassing. If we create it with brackets, we delete it with brackets, right? We want to get rid of the whole thing. So that gets rid of the memory. And then to be safe, we should nullify the pointer so we don't come back and accidentally try to use it later on in our code. Okay. So just some basics for you. And a lot of what we're going to do in this class is going to be dynamically allocated because we don't know ahead of time how big the problem is going to be. So, but fortunately, mostly we're going to be allocating arrays. So this pattern we'll keep using over and over and over again through most of the course. Okay? We might change the type from int to float, or it might be an array of stacks or an array of whatever that we'll design in some class, but it will still be an array. Okay. Questions on that part? Okay, well, we'll see that in play as we go forward. Okay, and it's worth saying that these things never go away until your program stops. So one of the reasons we have AAA video games that crash and servers that crash and Chrome browsers that crash, is because somebody allocated some little mini thing every time a web page opened, and they didn't quite forget. They forgot to free it, to delete it. And so we just have a little memory leak, and the OS just eats up more and more, or the program eats up more and more memory until it exceeds some boundary, and then we have to crash. So usually those leaks are the result of non-deleted dynamic memory allocations, but they could be other things too. So now, those were integers, right? Creating arrays of integers. We need to create lots of instances of bigger boxes of stuff like classes. So a person class in C++, the easiest way to think about it is, and it's very similar to a struct, but we're going to work with classes pretty exclusively because it's just a better version of a struct, for those of you who know what a struct is. But it's going to have two curly braces, a semicolon at the end, which is a little strange, a private and a public area, so we can hide data. And my analogy is the private data is kind of like, a friend of yours opening up the hood on your car and tinkering around with your carburetor instead of just getting in the car and using the steering wheel and the key, right? So yeah, maybe you want to let them do it, but maybe you don't want to let them do it, right? So when we design classes, we're going to have private data members that mostly we don't want the public messing around with. They're kind of for us. And our public area, maybe we have some data members there, but for the most part, we're going to have methods in our constructor there. And that's what we call our interface. That's how we want most of the world to interface with our class, through the constructor and through our methods. And that also happens to be kind of one-to-one with this idea of an abstract data type. If we want to push something on the stack, we're going to have a push method. If we're going to pop something off the stack, we're going to have a pop method. And that'll be done really through our interface, which is our methods in our class. Okay. So we'll be using a lot of that. Now, just to look over at these other languages, you can see Java's pretty similar. Some of you are pretty capable Java programmers, so you kind of recognize that. So a lot of similarities there, capital string versus lowercase, but you can kind of see the ideas are pretty similar, okay? Now we go over Python, it's like, couldn't you have just followed the pattern? So I do like Python, but the constructors are a little bit strange. So it's called double_init, and it's got a self in there, which we won't go into. But, the idea is the same. You construct an instance, and then you have methods that operate on that instance. And we'll be definitely following that through this particular course, okay? Now, one thing we got to do a lot of is create these instances. So remember, blue variables are automatic. So person P is like saying int X. It's just that person needs some constructor arguments, Ollie Smith. But I'm really just creating an int X that's going to go away at the end of its scope, okay? So in C++, it's kind of the way they designed it. They want instances of a class to kind of look like a native type, float X, string name, person P. It's just that sometimes we got to give those variables some constructor arguments, and that's what we're doing there. But then, as many of you know, we can say P dot, right? If it's a blue P, right? It's not a pointer, it's an actual instance, then we can say dot. If it was a pointer, we'd say arrow, but here we're going to say dot print me. And now we're calling the method that's part of the person class, and we don't really give it any arguments, but it's operating on this person right here, of course, right? So dots in C++ deal with instances, where in other languages, really dots go with pointers, because many other languages like Java and Python are fundamentally pointer based. C++, P is an actual box of stuff. And so we'll see that the dot for us really is more happening when we haven't created any pointers. Okay. And we'll get to that arrow thing here pretty soon. But we can reach in and change the public data members of the class, call the method, right? Can verify that the change happened. But of course, we can't access the private members. So if we go back and look at that private area, we can't do that stuff. Okay? And then we can create another instance, John Q public, and on and on. So that's how we create instances of a class. And we just have to give them the necessary constructors in order, or constructor arguments to satisfy the class. Okay. So we'll come back to the dot versus arrow thing for instances versus pointers, but this is the way we'll kind of start out with that dot thing right there. Okay. So let's talk a little bit about this idea of the difference between the interface and the implementation. So abstract thought. We go to a restaurant and we don't get to really talk to the chef or the people in the back, right? So we are the user of the class, and the interface is our waiter, and there's stuff going on in the kitchen, but we're not really seeing that. And far as we're concerned, we don't really maybe want to know, how they make the sausage, as they say, right? So we have an interface where we set and get things, right? We ask for things, we set things, or we change things that get stored in the class. We set our order back, etc. Right? So that's our interface. And very often that's one-to-one with this idea of an abstract data type. Push a pancake, pop a pancake. How does a pancake get stored? I don't know. That's separate. Like, we're not going to worry about that right now. That's what we mean by interface. And usually that's one-to-one with this idea of an abstract data type, but not always. Not always. Okay. So, but it does some nice things. It allows us to separate implementation from interface. So implementation is, hey, what data structure are we going to use for those pancakes? I don't know, a couple things we could do: linked list, arrays, all sorts of stuff. And occasionally we want to reach behind the waiter and get some private data. So maybe we know about some stuff, or we design a backdoor into our class for that to happen. But, that's probably just for us in this class and not for the real world out there. Most classes don't let you muck around with their private data members, because if you were selling software, it's kind of like having people, mucking around under your engine. Okay. So here's a car, right? Our interface, just to kind of drive this home, right? So I have the implementation hidden from us. How big is the gas tank? I don't know, right? But I want to put the car in drive. I want to, find out, how fast are we going at this particular moment. And you can bet it would be fascinating to crack open a Tesla or whatever and see what its, object-oriented design was for the drive system. I would hope it would be very clean and very well thought out. But you can imagine something like that really does exist. And all the time, we're probably changing or upgrading the implementation behind the interface. So these people over here don't have to change how they drive the car, right? When the Tesla updates its software overnight, for the most part, it doesn't affect the driver, although I've heard some stories, but it might change the software completely underneath, okay? And that's a good thing. We don't want to affect the way the user or the user of the class has to change in order to deal with changes we make to the implementation on the inside. So we're shielding our class users from changes. So if you were a third party software company selling your classes to thousands and thousands of people, if you really want to upset your customers, you just say, sorry, throw away all your code and rewrite it. We changed this thing, right? You don't get to do that very often and sort of survive, right? So we're going to look at that with most of the algorithms that we're going to tackle this semester are going to be wrapped inside of a class. So the class tends to be one-to-one with the algorithm, and the interface is all about how we solve particular problems. And in a lot of cases, our constructor will handle the vast majority of the things. We'll show you what we mean with that today, okay? But imagine, changing the size of the gas tank inside of our car, right? That's something we would want to do without requiring everybody to rewrite their code for driving the car, right? We should shield the outside user from that by a good interface design, okay? So we call that an abstract data type, and it basically helps us separate the algorithm from the data structure, or at least, keep them relatively decoupled, okay? So it minimizes the impact of changes. So we're going to study this first with stacks and queues, but we'll go on to use it throughout the rest of the semester. And I will tend to refer to this as an ADT, though I do hate acronyms, but it's one that's kind of hard to escape. So abstract data type is this idea of a general description of the problem, okay? Now, out in the real world, we tend to hear these things somewhat used or abused. Abstract data type, as we've described, API or application programming interface, could be kind of exposing the interface for a class, but it's not always going to be one-to-one. Class interface is a little bit closer to being one-to-one with the idea of an abstract data type. But people use these phrases somewhat interchangeably out there, okay? And it really just describes how we access the data and hopefully doesn't say much about the underlying implementation of the data, okay? Okay, so let us begin and dig into a few examples. So here are some things that have data structures inside of them, right? Last name, first name, array of wheels. So none of these really speak to a problem per se. They are just the way we're storing the data, okay? So all of these things are very easily described as the data structures or the specific implementation of the data structures, not the interface at all, just kind of how are we going to store all that data. And we have a lot of flexibility on how we might do that. The interface, of course, is our constructor and any methods that we're going to call, like print me or, set something up, initialize some value. Okay, so that's going to be our interface. Okay. So, and quite literally, when we're talking with software engineers, they'll talk about an interface class, and that's all about those methods in that constructor, not the underlying data structure for storing data. Okay. So here's our person again, right? And there's our, data structures, simply strings, and our constructor method. That's our interface. Okay. And it makes sense that the interface is public. We would want our interface to be public. That's how we want everybody to interface with that class. Okay. So apologies if some of these things are a little bit obvious, but it's a weird topic. So I just want to make sure we're all well grounded. Notice also here that sometimes in class, you'll notice I just terminate my constructor with a semicolon. So what am I saying there? I'm saying, hey, this is the blueprint for you or me to go implement later on. So for those of you who are familiar with the idea of a .h file, or you've heard of that in C++, generally those are the files that have these blueprints. So when I first started out in computer science, our professor would be like, here's your .h, good luck, and you had to go build that thing, right? So that's kind of the blueprints for a class that we can go finish relatively easily, okay? So to compare that, of course, if you see the curly braces with your methods and your constructor, then even if it's all piled up on one line here, okay, that's the fully operational class right there. Okay. So I'll use both of these interchangeably throughout the class to kind of talk high level about the interface versus a specific implementation. Okay, so let's get to the heart of what we want to do today, stacks. It's a pretty approachable idea. We all have dealt with stacks in our life, and they are pretty fundamental to all the software we use. So stacks are an abstract data type, and we can just talk about them in terms of the interface. Now, I will sometimes use this notation, which is very C++ as well. The class name is stack, and the method inside of that class name is push. And we may encounter this during the semester, but it really is just my way of using C++ syntax to be more concise. So name of class, scope resolution operator, method within that class. So if I want to push this thing, I'm just going to push a value in there. And as you might expect, right, they're going to pile up and I cannot deal from the bottom. That's really the classic definition. So all I can do is pop. Okay. So popping does what you would think, right? And we can test other methods throughout that time to see maybe how big the stack is or if it's empty or not. But that's really it for the stack. Okay. Seems like an incredibly simple idea, right? And it really is, but very powerful. So not empty, pop, pop, pop. Now we're empty. Okay. And the oldest thing in the stack is on the bottom, of course, and the newest thing is on the top. Okay. So if I want to know the size, probably we're going to keep track of that size as a data member of the stacks class. Rather than counting the stack every time somebody asks us, it's probably much easier to just have an integer in our class, of course, and increment or decrement that integer every time we add something to the stack. So we could do it by manually counting, but that would be a little bit wasteful to do that. Okay. So at any time, I should be able to say get size and find out what I got there. Okay. So these are just basic aspects of our interface. Right? So what are some things we can do with stacks? Seems like pretty simple. How far can you go with such an idea like this? But they're fundamental to pretty much everything. They're part of our virtual machine languages. The history in your browser is kind of a stack. We'll see that we can reverse a list of items using a stack. That is part of several algorithms we'll study this semester. It's just one part. Function calls use something called a stack frame, where we just push pancakes on the stack, but each pancake is all the variables inside of a particular function. So when we do recursion, we are stacking lots of stack frames on top of each other for every recursive call to the same function. So somebody's got to be able to remember that stuff so we can unwind from recursion, and stack frames are the way we actually pull that off, right? With the same function call, just lots of different collections of frames of variables. And the list goes on and on, right? There's lots and lots of ways to actually use these things. So very often, and this is an easy question, but one that gets asked is this a last in, first out, or a first in, last out, or what kind of thing is this? But if you think about it, the last thing that goes in is the first thing that comes out. So these are often referred to as LIFO structures, or it's a LIFO structure, last in, first out. It's really just trivia. You can probably, everybody can relate to that. Probably that's what's going on. But we'll see that there's something called a FIFO. That'll come up in our next lecture for queues. But in this particular case, it's a LIFO. Okay. LIFO stacks and FIFO queues. Okay. First in, first out is something we'll see in a queue on our lecture on Thursday. Okay. So there's some stack examples. Let's take a look at one good, fun algorithm. Let's say, and this is a fun one to write if you ever wanted a side project. So you can evaluate that question with two stacks. So Dijkstra came up with this first. So if we encounter a value, which I've got here in purple, we're going to put that on the value stack. And if we encounter a green operator, we're going to put that on an operator stack. And if we encounter the white left parenthesis, we'll just ignore that. But when we encounter a right parenthesis in orange, we're going to pop something from both stacks. Okay, pop an operator and two values and evaluate that and then put it back on the value stack. Okay, and I'll show you how we do this. We'll go through this here in a second. But after everything is processed, the thing that's left on the value stack is the answer to an arbitrarily long equation, which is pretty cool. Okay, so let's take a look. So here's our equation, and we'll modify this one on the right over here, but we'll have this one on the left for reference, okay? So here's our stacks. So I ignore the first parenthesis, put in the 1, put in the operator, ignore, put in the 2, put in the operator, put in the 3. Now we've hit a parenthesis, so it's time to process two operands. So we take the 2 and the 3, we add them and put the result on the stack and keep going. Operator goes on, ignore, 4 goes on, operator goes on, 5 goes on, process, right? So 4 times 5 is 20. There we go. Time to process again. That's 100. And then if we got anything left, we just sort of pull them off until we're empty, right? And there's our 101. So it's sort of like, if you ever heard of postfix notation, right? We're kind of creating a postfix notation in stacks. But it's just a nice way to demonstrate how useful these things can be as part of an algorithm. Okay, so that is one of Dijkstra's many algorithms. Okay, so here's our methods that we want to put in our class, and we're going to explore this here in just a second. We're just sort of fleshing out what we want, right? We want to push a string if it's a word kind of stack. Push pop, get size is empty. Don't need much more than that. Okay. So we could use an array to hold the stack. So we'll look at that here in a second, right? And if we run out of space in the array, we got to have a strategy for that. So we'll talk about what are our strategies and what is the ramification of that strategy, okay? And for our notation or our convention, we'll put the oldest thing, the first thing we put in the stack is going to be at the left. So you got to kind of imagine rotating this thing so it stands on the end on the left side, right? So newest is on the far right, oldest is on the left. And this does get confusing. It always confuses me, but we'll see how that goes. And then we have a linked list approach, which is I'm just going to have some way of holding a number in an instance of a class. We'll call that a node in this class for the semester. And we'll just link those things together. And there are some pros and cons on both sides of these data structures we'll explore here just briefly. Okay. But those are our kind of two approaches. And people on the outside should not need to know that that's what we're doing. It should be somewhat of a secret, you know, in a way, right? It shouldn't bother them what we're actually doing. But let's look at the stack array class. And this is where we'll start digging into some code. So we're going to need a data structure there, right? TBD. But we're going to need a constructor, and we probably want to initialize the size of the array in some way. Maybe we know something about how big a stack we're going to need, so let's give our constructor an opportunity to solve that problem for us. So if we say, hey, you know, give me something that's big enough to hold 10 things, then that's what we want to do. We're going to have a pop, a push, and a get size, and it is empty. So pretty generic so far, with the exception of this little change there, okay? Now we're gonna, as you might guess, we're gonna need for an array, a stack array class, we're gonna need a dynamically allocated array there, and it's gonna need to be as big as this right here, because that's what we're being asked to do. So we'll take a look at how we actually do that for this string type class, okay? Even though we have not officially implemented anything yet, we kind of have an idea of what our strategy is gonna be, okay? So here is how we want to do this in main. So sometimes I find it helpful to just sort of think about main first. So int x, right? Stack array, my stack. Same kind of thing, except we give it the max size, and then we start pushing words, okay? So our stack array for the moment is just going to be a string type stack, okay? So we're kind of locking it down to be a string type stack. So push, 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 pop. right? And if the pop returns us something, we can send it to the cout, which is good. So cout my stack pop, get the size, etc. Okay. And for those of you who have not used the ternary operator before, I won't try to, hit you over the head with it, but it is very nice in situations like this where we say, hey, are you empty? Yes or no, right? And if it's yes, then the empty goes into the stream. Otherwise, the not empty goes into the stream. So this is just my way of taking a binary method, true, false, and turning it into a word. Just a little, I wouldn't even call it a hack. It's just a way of using that if else. So you'll notice there's a question mark and a colon. Those are the kind of telltale signs of a ternary operator. Okay. If this is true, do this. Otherwise, do that. Okay. So you'll see that every once in a while in the course. Okay. So that's what's going to go over there if that's true. All right, so let's dig in and do it. So here's our private maximum size. There's our private pointer. We'll call that p stack, string star. It's going to be pointing to a dynamic array of strings. Okay, maybe a little bit strange to see it that way, but we'll see it come together here in a second. How many things are in the array currently are 0. And then here's our constructor. So we want to hold on to what comes through the arguments. So that's going to go into our data member. And sometimes I'll use that underscore just so we don't confuse those two things. Many of you know that. And I will dynamically allocate my stack. Okay, p stack equals new string max size. Okay, so now we're ready to kind of write the rest of those methods. Okay. So implementation and our implementation of the interface down below, okay? Which is primarily the constructor so far, and we're going to do this right now, okay? So let's go back to main and see what's happening. So notice that the orange box is the instance of the whole class stack array, okay? And it separately has a pointer that is pointing to, or will be pointing to, a separate chunk of memory at a separate address. So what we're doing here is creating somewhat of an exotic data structure, which is the home base is the stack array instance, but it's got a pointer reaching off somewhere into memory, we don't know where, and holding on to a little chunk of memory that we'll use for storing our numbers. And it's not allocated until we call the constructor, okay? And we'll learn about how to deconstruct that, but more in this class, we're more interested in the data structures than the pure C++ stuff. So that's our private stuff. Current size is 0, so there's nothing stored in there. But notice that the current size also points to kind of the, not points to, but it's the ID of where we should put the first thing, okay? So we're going to slowly push stuff in there. And as we do, right, our current size is going to move out to the last available position, or maybe even off the end, right? So if current size goes beyond the max size, then we're actually, or is equal to the max size, then we know it's time to allocate some more memory, okay? But that's our basic strategy. And the oldest thing is over here, and the newest thing is over here, at least as far as our array goes, okay? So that's what we're going to do, okay? So if we go beyond, or if we say we are now equal to the max size, well, we know it's time to resize that array, okay? So we can figure that out pretty easily. So let's take a look at this actual code and have you guys try to write the print stack via array. Now, I know this seems really trivial, but we're going to print out members of the stack from the newest on the left to the oldest on the right. So we're going to print in reverse array order, which you might say is silly, but we're going to just do that for now. And we're going to use the pointer p stack to access that dynamically allocated array. And we're going to use the current size data member to determine, like, where do we start, right? And if the current size is equal to 8, you aren't going to print beyond the range of array positions, okay? So we're just going to go 0 through 7 if our current size is 8, Okay. So let me put this up for you, and I would recommend you trying to do this because your lab is going to be based around this. So let's just look at the code here real quick. You guys can click in if you want. The link should end with an RK8, and you can get that in Canvas if you want off of this. But basically, you're going to sort of be in the middle of this thing. You can kind of see our constructor here, right? And our push, relatively straightforward push, right? So this is our push all the way down to here, okay, like so. So P stack current size equals whatever somebody gives us, increment the current size. And if the current size equals the max size, let's print a little warning because that means, we're about ready to walk off the end and corrupt memory, okay? So that's our push, okay? Clear my scribbles there. And you'll see this in the code if you take a look. Pop, right? Is it empty? Notice this is what I call eating your own dog food. We're calling our own method here. Why would we do that? We could just go for the private data member. But one nice thing about calling your own method is that you can come back later and change the name of your, your count number or your count variable, and it doesn't break all your methods. So it also helps us test our own public methods by using them ourselves, okay? So it's okay to call your own method from inside of the class. You're just reaching up and calling that, reaching down in this case, calling the isEmpty method right there, okay? And then we decrement size, etc., and we return what just got popped. It's like, hey, return a copy. Now, I've used this phrase before. C++ is a copy-centric language. So when I say return P stack current size, let's say that's Jeff stored at current size 7 for some reason. We're making a copy of that string and sending it back. We're not sending a pointer or anything. We're just copying that whole string, sending it back as the return value of this method. So we are indeed making a copy, not referring to it by some address or some pointer. Okay? If this said string star up here, that would be your little clue. It's like, this thing's returning a pointer to something, but there's no star there. Sorry to regale you with C++ syntax, but that's kind of how we're going to live for the next couple weeks, okay? So that's our pop, get size, and print stack. So if I'm going to print the stack, I want a loop that goes from 1 less than the size, the current size, down to and equal to 0. So let me give you the code for that, because I always find when I try to actually write code and talk at the same time, I just make it worse for everybody. But here's our print stack, okay? So we want to count backwards from size minus 1 while I is greater than or equal to 0, and just print the stack, right? From newest to oldest, okay? So we're kind of going in reverse. This is print left to right, but I think it's right to left. So I got that back. We're going to go from newest to oldest. So this is backwards right here. It should go from right to left. That's what I really meant there. Okay. So that's going to do our print. Okay. So you should be able to run this program relatively easily, interactively, and just build your stack up until you exceed. And if you go too far, you'll probably crash the program. You'll get the warning and it will probably crash at some point. I think we didn't put any really safety features in that yet. Okay. So our data members, for folks who are maybe still a little rusty on this, are like local variables. When you're in a method for the class, anything in blue, if you will, is just free reign, right? So I'm in the print stack method, but I'm also inside of the class, which means I can refer to its data members right here, okay? So we need to remember that we don't need to go, creating another counter or variable. They're all right there, okay? So it's relatively easy code to just pop that in there, okay? So if this is our current count, we're going to start at I minus 1, right? Because we got 5 things, so that means they go from 0 through 4. So now we're looping from current size minus 1 down to and equal to 0. Okay, so that should be what your code is doing there. Okay. So that's just kind of getting to know a data structure. And I highly recommend whenever someone throws code at you, the first thing I do is try to print out the data structure. That's the first thing I do. It's like, okay, let's see how this thing is structured. I'll print it out on the screen as best I can, and that's going to teach me how to get around. But let's take a look at how we deal with the impacts of doubling the array. You might think this is just really not a very smart thing to do, right? We run out of room and suddenly we got to like allocate more. So a naive approach would be, okay, let's make it one bigger, right? So we copy all that stuff over and we throw away the other thing. And so we've kind of paid a cost of n, you could say, for just that one change. So n is the size it was at that moment in time, right? And then it became n plus 1. So kind of paid a cost to do that. And it felt okay at the time, but probably we're going to run out of things pretty quickly if we're in growth mode, okay? So the plus 1 approach is not great. And if you were to sort of think about it, right, over the life of this data structure, we're going to do one copy, then two copies, then three copies, then four copies. So if you add up all those copies over the life of the data structure, you're kind of doing an arithmetic series, okay? So I'll get to that here in just a second. But basically, every time we do this, it's an arithmetic series over the lifetime of that thing growing. So because of the number of copies are always going to go up by 1. And that's really quadratic. So that's kind of a hidden cost. It feels okay in the moment, but really it's pretty expensive to actually do that. It's pretty slow, okay? So it's this way, right? Which if we use the arithmetic series, equation again, if we really look at the old size to the new size and how many accesses we need, this is the number of copies, right? So adding all that stuff up is really just the same as an arithmetic series, which is an n squared kind of proposition. So not great. It's that bad quadratic thing again. So we can do better. And, there's various ways to actually decide how to do this, but probably the easiest way to do it and make a good analysis of it is to double the size every time, okay? And that gets a little bit easier to assess the cost. So we can kind of hedge our bets here and say, well, we're pretty sure that powers of 2, we're eventually going to get there. Now you could argue like if I had 1 million and I double it to 2 million, maybe that's a little extreme. But this is a good way to get started. So how do we assess the cost of doubling over time? So just a little bit more math and then we'll get back to the code. Basically, I have 1 and then I have 1 times something and then I have 1 times something to the next power. So essentially, it's a geometric series. And we have an equation for that. It's r times 1 minus r to the number of terms minus 1 over 1 minus r. Getting a little messy. But we can put in the value for r because we're doubling at 2, right? And factor things out a little bit. And so for 13 doublings, right, we're going to be somewhere in the neighborhood of 4096, okay, for a stack size. That's going to be 8,190 array accesses. That's linear. That is 2n. So if this was the size of our array, right, and we achieved it by doubling from 2 13 times, right, 2 to the 13th, I think that might be it, we're really still at a linear cost. So we've gone from quadratic to linear. And it kind of makes sense, right? It's intuitive. It's like, well, rather than have to like add another thing every time, I'm just going to double it, double it, double it, double it. But what's interesting is the analysis kind of is easier to see when we work with powers of 2. It's like, oh, okay, so somewhere between going by 1 and going by doubling is, approaching a linear type of cost. Okay? So it's the insight that's useful here. We might not actually double it all the time in the real world, but we can kind of use that as a nice way to analyze the size, okay? So here's just another way of looking at that, right? So 1, 2, 4, 8, 16, right? We add those things up using geometric series in the equation. We essentially get our linear kind of result, okay? And it holds up no matter how many times you grow this thing. Okay? So a lot of times we will, if we're working with some structure like an array, we'll take a strategy like doubling, right? Or cutting it in half at the right times to minimize the impact over the lifetime of the data structure. Okay. So those are kind of just some tricks. Uh, okay, and you can kind of work through the math if you want, but essentially, there's that. This is an important identity, right? Sometimes it just shows up. To raised to the power of log 2 base n is always going to be n. Okay, that's a handy one. Okay, so that shows us we're really just dealing with linear behavior here. Okay, so a little bit of math. Okay, now when we cut things in half, it turns out that, if we cut them back in half every time we approach the midpoint, we might be flipping back and forth. So sometimes this is called hysteresis, where we cut it in half, then we double it, we cut it in half, we double it. The better strategy is just to wait until we get down below maybe 25%, and then we cut it in half. It's like, oh, you're only at 25% capacity, so I'm going to cut you in half, right? And now you're at 50%. So you can play all sorts of games with whether it's 25 or 35 or whatever, but we'll sort of take a look at this in implementation here in just a second. Okay, and it's generally to avoid our thrashing. Okay. So once again, I'm going to kind of fly over the top a little bit. I encourage you to look at the code. I'll show you the solution here. It's not a lot of code, so it's pretty quick to implement. But whenever we push something and it exceeds the capacity, we're just going to call a resize method, a little private resize method to do a allocation and a copy and cleanup. Okay. And then we'll watch when our pop drops below 25%. Okay. And then we can kind of run that test. So let's take a look at the code, right? So here's our resize. If somebody says, hey, inside of our stack class, I want you to go to this size, right? So all I got to do is first allocate the new buffer. Okay, so temp star, it's a string pointer, an array of empty strings. Okay. And I say, keep going from I till you're less than size or less than new size. Right? I don't know if I'm shrinking or growing here. So this handles both cases, right? I'm going to copy as much stuff as I can from pstack into the temp. Okay. And then I will delete the pstack and I will update the pstack to be pointing to, I'm going to steal the pointer. I'm going to steal this pointer and store it in my pstack pointer for the class, my private data member. So now I have my pstack updated. Temp was just a temporary pointer that now will go away once my method is done down here. Okay. And I can update my new size as well. Max size equals new size. So this is really all we got to do, whether we're shrinking or growing. Okay, just that little method right there kind of does it for us. Okay, so let's see where that fits into our kind of other methods here. It's really not too complicated. I really do hate this thing. I have a love-hate relationship with it. Okay, so let's see if we got the other code up here. So here's push. Okay. So if the current size is equal to the max size, it's time to double. So we do a little feedback for ourselves. We resize to 2, and then we go ahead and push the S at the current size. Okay, just that simple. So the push is just, of course, copying into the next available position and incrementing the size after the fact. Okay. So that's our push. And then our resize from pop. So we reduce the current size. We pull the word out of the array, right? And then we check to see whether we need to shrink it, okay? Now notice, just by the way, if I have an array of, this is my stack, right? And it's got the letter A right here, right? And I shrink the current size, I don't need to delete the A from the array. I just sort of pretend that's all I really have, right? So we're not really ever deleting anything here. We're just shrinking the size and ignoring what's probably still stored at that part of the array. But if we need to shrink the array because it's gotten to 25%, then we can just call our resize with half the size and we're all done again. So that's our pop, right? And dealing with that on the fly and returning what it is we just popped, okay? So get a copy, return that copy as a result of the string pop method, okay? Now, that's our array. A little bit messy dealing with that stuff. So bear with me. We're going to go through the stack linked list, which will bring us a little bit of, freshening on our pointer stuff. So both of these are good C++ review things to go back and look at. But a different class, pretty similar, it's going to have a different data type there and pretty much the same methods and a simpler constructor. So we don't really have to decide ahead of time how big our stack is if it's a linked list class, right? So we'll just kind of have something with no arguments for our constructor. So let's take a look at what that looks like. And this is an important thing in C++. It's annoying. That is like int x, okay? Or, string first name. It is calling the constructor with no arguments. It's really tempting to do this, my stack parenthesis, right? But that is not what we want to do in C++. It's more like int x. Give me an instance of my stack and start pushing stuff, okay? So pretty much the same as our array class, but without those parentheses, okay? Okay. So stack linked list. So we create it, right? Pushing, pushing, pushing. This is what we want to do. We want to have a head pointer, and we're going to need a little train car. We call those the nodes, and we'll create that class here in just a second. But it's going to hold just a word and then have a next pointer. So I think everybody's probably who's been through my class or any of the other classes here has done linked list already. But that's what we're going to do. We're going to have a head variable as a part of this private data member in that class. And we're just going to use that to push nodes or instances of the node onto that linked list. So we're going to need two classes. We're going to need both the linked list class and another class called the node class. And these two are going to work together, okay? And we'll just sort of build that thing by pushing and popping from the head, okay? Now, everything about this is pretty straightforward except for one thing. We can't really access the bottom of the stack efficiently in a linked list. This is the downside of using linked lists, or one of the downsides. You could go all the way to the bottom and build some structure, but at that point, you're not really dealing with a singly linked list. You got to add a double linked list to it, which is okay, but that's going to cost you a little more memory. And so there are some trade-offs involved in that. A classic stack does not have a double linked list. The whole idea is it's really efficient because you never need to go in the opposite direction. So typically a stack would not try to print in the reverse order. Moreover, it wouldn't even let you peek at the bottom of the stack or go in reverse. A lot of them are optimized so you just can't actually do that ever. Okay? But we can build it ourselves and do what we want. So here's our node class that holds a word, okay? There's my word. There's my next pointer. Of course, it connects us up to the next node. So it's sort of, like that, right? And we'll set that next to nullptr, although more and more it automatically gets set to that, but I always like to be careful. And there's our constructor. We get a word. And then we set our pointer to null again, just in case. It's not really necessary. If you've done this, you don't really have to do this, but I always try to be careful because it saves you hours late at night when you're chasing down bugs, okay? So there's my linked list, and now we can kind of build that thing, right? There's our head, current size is 0. There's our stack, or our constructor rather. and the push and pop are going to be classic linked list steps. So just a little review for everybody. If I had something already in the stack called foo and head is pointing to it, and I want to connect another thing on top, it's a two-step process. First, I create the new thing, right? Then I'm going to redirect the next thing on the new thing to point to what the head is pointing to. So temp next equals head. That's what that's doing. Temp next needs to point to what the head is pointing to. Okay. So we'll see that in code here in a second, but that might throw you a little bit. Temp next points to head. And then head equals temp. And now we can throw away the temp variable because we've got our updated linked list. Okay. That's our classic push into the head of the linked list. And it's like the pancake, right? Foo is the oldest pancake, and then we put on bar, and we can repeat that over and over and over and over again. Okay? So that's our push, okay? A pop is almost a little simpler. So let's say we have two things. So we're just taking some simple cases, right? Okay, if I want to get the bar out of there, I need to hold on to it first, set the head equal to head next, right? So head equals head next. Notice that little arrow in there. So we're dealing with pointers now. So we're no longer going to say dot next. We're going to say arrow next. So head equals head next. And now we're kind of removed the bar. True, bar is still pointing at foo, but we're going to get rid of this. So all of that's going to go away anyway, right? So we steal the string from the bar, and then we blow that thing away, and we're done, right? We just return the string. Okay? So we need to explicitly delete what this thing is pointing to here, so it goes away. Otherwise, we have a memory leak. Okay? So it's a little annoying. It's admittedly very low level stuff, but many libraries are based on this approach, right? All the vector stuff, the list stuff in C++ libraries, probably Java stuff, has a lot of that stuff. So let's just zoom in on the code real quick, and we'll summarize the solution and get you into lab here. So there's our constructor. There's nothing to do, right? We got nothing, right? Because we got a null head pointer and we haven't added anything yet, and our size is 0. Okay. So when we push, we're going to just create the new node, right? That's going to be our new head. We're going to say new head next equals whatever the head was. And even if the head is null, that's okay. And now we're going to say, okay, the real head points to the new head and increment the size. So this is a classic pushing one pancake onto a linked list. Okay, just that simple. So whether head had 0 things or a million things, this will always work. That's the nice thing about pushing into the head. Okay, we don't have to go looping or doing anything at all. Okay, so that's our push. Let's take a look at our pop real quick. Okay, so our pop, hey, if it's empty, can't pop anything. So how am I going to get out of that problem? Because I got to return something or C is going to go all sideways on me. So I just return an empty string, okay? Safest thing to do. If you don't return anything, things could go badly, okay? Depending on the data type. Otherwise, decrement the current size, grab onto the head, copy out the value because we want to return the word, advance the head pointer, and then delete what was the old head, and then return that string, okay? So also doesn't need to happen with any looping, which is nice. Okay, so we're pushing the head to head next, and we've held on to the old head here so we can delete it later on down below. I should have colored this pink as well, so there's a little confusing coloring there. Okay. Okay, and then the last thing we're going to do, like I said, printing out a data structure is the best way to get to know it, right? So let's take a look at how we would print out our stack from the top down, okay? And I'll skip over the main part right here and just kind of jump into the practice problem. So we want to use the head member of the stack to start printing, but we don't want to change the head. It would be very bad if we change the head while we were printing, because it will never be able to get back to the beginning again. So we need a temporary node, like current node, to actually hang on to the head and then use that to traverse through the node. So we're going to say if the current node next is equal to 0, well, then we know, we shouldn't do any more printing. So that's probably one way to think about how we stop printing. Okay, but let's take a look at the solution to do that. Okay, and you guys can code along or come back to this later. So I'm going to grab onto the head, and I'm going to say right off the bat, if that thing is not equal to null, I'll keep going. Okay, I'll keep going as long as that's not null. I'll print out the word, I will advance to the next thing, and I'll go back around. And that's really all we need. Okay, and we can get fancier and say, oh, if it's null up here, I'll print the word empty, right? Because this will just do nothing if it's a empty list. But otherwise, that's perfectly fine. Okay. And this is the critical part. We got to move to the next thing each time before we loop around. Otherwise, you just print the first thing over and over and over and over again. Okay. And if this is null to start, it's never going to enter the loop, and we're just going to get a silent ENDL at the bottom. Okay. So again, notice because temp is a pointer, right? We use this to follow the pointer into the box. So I like to say this is like a box. And if this is temp over here, right? If this is temp over here, temp arrow next means go into the box and look for the next field and ask yourself, what is that pointing to? Oh, that's pointing to something over here, right? So I'm saying T equals T next. So that means T ends up pointing over here, or temp ends up pointing over here, okay? So a little bit of a head scratcher if you haven't done it before, but that's our classic. It's like, I say it's like X equals X plus 1. It's temp equals temp next with an arrow, not a dot, okay? A little bit backwards. So stack performance, kind of summarizing this, and we'll get you into a real quick lab. So if we do an array implementation, push and pop is, linear over the lifetime. So 2n is incorporating that idea of doubling the array size every time we exceed capacity. So over the lifetime, it's 2n, right? Assuming that the ending size is n. So it's kind of a weird way of assessing it, because for the first time, we're talking about lifespan, not like, hey, here's some things I need you to deal with, right? So we would say that over the lifetime of it, reaching n, we've cost to 2n if we do a doubling. Is empty, get size, these are constant calls. It doesn't cost us anything. Printing is linear time, of course, because we got to print n things. Oldest to newest is also linear time, so that's an advantage of arrays if we wanted to do it. And there's no pointers, so it takes less space per data item for sure, which is a nice thing. Linked list, we have constant time always. We never have to worry about, doubling the size and copying stuff around, so that's a huge benefit. The rest of this stuff's pretty similar. Print oldest to newest. And unfortunately, we can't print backwards, but do we ever really want to print the stack backwards? Maybe, but not usually. But it takes more space because of the pointers, 64 bits per node, because that's what our pointers cost us on a modern architecture. So yeah, it takes a little bit more memory, maybe a lot more memory if you're just storing a character, right? Paying 64-bit cost to, point to the next character is probably an expensive proposition, okay? But those are our two approaches, and, printing is just kind of an observation, not a critical difference between them. Okay? So that's our kind of first introduction, top to bottom of what is an abstract data type, how do we build it, maybe what are two different data structures we can use, and what are some of the ramifications of those choices. It's not the end of the world, but we'll use that same analysis. We go into some of these other abstract data types. So for our lab today, it's going to be just show me that you know how to use this data structure to do something interesting. So you don't have to write anything except in main. So what we'd like you to do is use this unchanged data structure that's already there in that link, and you can get it off of Canvas and do it in any IDE you want. But create a stack, unload the array in natural order, right? So push, 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 right? And then put it back in natural order, right? Oops. Oh, I thought I fixed this animation. Sorry, this animation is broken. The 11 goes here, the 2 goes here, the 33 goes there. So I did not update my slides properly. Very sorry about that. But that's what that should do, right? That is a classic use of a stack, is to reverse something in an array. We put it in the stack, and then we put it back in the array, okay? So apologies that this is doing it the wrong direction, because that is absolutely wrong. It should be the other way around, okay? So that's it. Yeah, it's a quick one, but it'll show me you know how to use C++ in main to create an instance. And if you need any examples, kind of go back and take a look at the practice problems, but that should be relatively quick. Next time, we'll talk about queues. So really similar concept, but whoever stands in line first gets served first. So that's a first in, first out, or a FIFO structure. And we'll build that one as well. And we'll use the words NQ and DQ, which are the traditional words when working with queues, to talk about putting somebody in line and serving them at the head of the line. Okay. And that is all we got for today. So I'll leave you with that. See you guys on Thursday. Have a good week. Thank you.